Influence of delays of self-oscillations in systems with limited power supply. Alishir Alifov, Mechanical Engineering Research Institute of Russian Academy of Sciences. Model equations of motion. Frictional self-oscillations are described very well by the model shown in Figure 1. Body 1 with mass m lies on the belt, which is driven by an engine having characteristic where is the speed of rotation of the motor rotor. The friction force T from U arising between the body 1 and the tape depends on the relative speed U. Under certain conditions, it can cause self-oscillations of body 1. The elastic and damping forces depend on the delay. We can see on the Figure 1 system model. Nonlinear differential equations describing the system's motion have the form given by the relations 1. Let's represent the characteristics of the force as functions given by relation 2. Here, T0 is the normal reaction force. Alpha 1 and alpha 3 are positive constants. Sin U is equal to 1 at U greater 0 and sin U is equal minus 1 at U less 0. Form 2 is widely used in practice. It was also observed when considering the problem of measuring the friction forces in space conditions. Solving equations by direct linearizations. Using the direct linearization method, we replace the parts in function 2 with the next function 3, b, f, k, f, v, n 2 and 3 are given by the specific relations. The symbol R is a linearization accuracy parameter, and the choice of the interval of its value R is not limited. It can be selected in the interval from 1 to 2. Equation 1 based on 3 takes the next form, 4. The desired solutions have the next form, where V is equal AP comes from. The solutions for determining the amplitude A, the phase zeta of the oscillations, and the velocity of the energy of source omega at U greater or equal V are as follows. 5. AD and U are equal specific relations. From 5 for A equals 0, zeta equals 0, follow the equations for determining the characterization of stationary self-oscillations. The amplitude is determined by the Nate ratio, 6. The amplitude of stationary self-oscillations is determined at U less AP by the AP is equivalent U dependence. The graph of the dependence of the amplitude of the speed over entire range of its change is shown in Figure 2 with tau is equal 0 lag and different delta lag values. The boundary velocity and the velocity at which the amplitude is zero are shown only for curve 1, delta is equal to 0. Similar velocities hold for curves 2 and 3. We can see in figure 2 the amplitude curves. For figure 3 shows a graph of the load on the power source over the entire speed range with different delay values. The forms and locations of the characteristics of and energy source are shown conditionally. The stationary speed value can be determined except 9, also by the intersection point of the curves as shown for the speed under the characteristic. In the case of the characteristic, depending on the initial conditions, it is possible to implement self-oscillations at speeds corresponding to points A, B, C. The third equation 5 gives an expression for U is equal to 0 to calculate the load S on the energy source. In the case of U greater or equal to AP, it has the next form. Equation 9 allows you to calculate the stationary value of the speed U. In the figure 3, we can see load curves for the power source. For figure 3 shows a graph of the load on the power source over the entire speed range with different delay values. The forms and locations of the characteristics of energy source are shown conditionally. The stationary speed value can be determined except 9, also by the intersection point of the curves shown for the speed under the characteristic. In the case of the characteristic, depending on the initial conditions, it is possible to implement self-oscillations at speed corresponding to points A, B, C. Stability of stationary oscillations. To determine the stability of stationary movements, we create equations in variation for 5 and use the Routh-Hurwitz criteria. The stability conditions D1 and D2 greater 0. In the case of U greater or equal to AP speeds, we have the next relations. In the case of U less AP, the first criterion 10 is almost always satisfied due to the dependence of AP is equivalent to U. The determining factor is the second criterion that can be represented in the form 11, where S is equal to specific relation taken into account AP is equivalent to U. Criterion 11 is fulfilled for a very wide range of characteristics of the energy source, which can be seen from the difference in the graphs of the source M and the load S in figure 3. Therefore, the velocity region U, where AP is equivalent to U, is the best for the relation of self-oscillations and the worst for elimination. Thank for your attention.